to some parts of the world. This is it. Again, I am a singer, eternal voice. So guys, this is our last topic for chemical reaction kinetics, which is specifically the enzymatic kinetics, dealing with enzymes. All about the interaction between the enzyme and the substrates, but we will apply the chemical kinetics point of view. That's why it is called enzymatic kinetics. Okay, so last topic for chemical reaction kinetics. Okay, this is more on biochemistry, but still applying the principles of chemical reaction kinetics. Okay, so let's start now. So in this manner, the equation that is very useful to enzymatic kinetics is the uh, Michaelis equation. Okay, Michaelis Menten equation. Okay, can you familiar with that, guys, or not? Okay. Okay. So Michaelis Menten equation. This one. Michaelis. The spelling is Weta and or Michaelis. Let's Michaelis Menten equation. Okay. The spelling is something on Michaelis like this. The spelling is like that. Michaelis Menten equation for enzymatic chemical reaction kinetics. Okay, like that. So dealing with enzymes and substrate, we will derive the equation for Michaelis Menten equation. Okay. Oh gosh. Oh, where's my other, wait for a while. Oh gosh. Okay. Now we have this enzyme. I have to put this in another paper so that we can have more space. So it's gonna be enzyme enzyme alone, concentration of an enzyme plus concentration of a substrate is equal to rate of forward reaction. Okay, ES like this, and the reversible chemical reaction, the arrow is going back like this. Okay, concentration of enzyme plus concentration of a substrate, reversible chemical reaction. If you see like this in a chemical reaction class in chemistry or in biochemistry, this is reversible chemical reaction. The arrow going there and the reverse arrow. So the top portion will be the rate of forward reaction, and the downside will be the rate of backward reaction. It's supposed to ES product from this reaction. Okay, this will produce also somewhere in the end of rate of forward reaction, the enzyme plus the product. So normally that enzyme also, ES, enzyme and a substrate, will still produce another product somewhere along the way here, which is splitting it into E plus P. The P is composed of many products, but we don't identify that anymore because it is continuous until the product's completion or the chemical reaction will just stop. So we are not interested with the letter P because we cannot identify that one. Okay, so actually there is still also another arrow, backward rate of forward reaction somewhere here, but our rate here is negligible and irrelevant already. Too small to consider. That's why the rate of forward reaction is enough, not the same like this. Because we cannot distinguish and recognize anymore the P here also. That's the only one arrow, rate of backward reaction in producing E. So basically there's no P anymore, but we don't know what's that all about. Okay, like that. So we need to put now here points to consider. Okay, let's say from here to here, like this. So let's say from here to here is our point 1. Okay. And our here from here is our point 2 to consider. We divide in segment. So this is 2. So, okay. In going here to here, this is 1, right? So there is a rate 1 corresponding rate low or the rate of chemical reaction or the rate low, so R1. So we'll put here R1 here. So when we have R1, we have also the corresponding K1 for this. Okay. So in chemical reaction kinetics, our rate of chemical reaction from this segment 1 here E plus S to produce ES. So K1, we will also put that here. So K1 here at the top. Okay. Now, since this is a reversible chemical reaction, we need also to put K minus 1 negative in going backward for this arrow downside. So K negative 1. Okay. All 1 because it is in segment 1. Now, what is your formula of R1? So R1, okay, R1 is equals to the rate constant K1 times the concentration of the reactants, which is substrate E and substrate S and enzyme. Concentration of substrate and concentration of enzyme. Okay, so K1 A and S. Okay, so this is only a bimolecular reaction because there are 2 products. We are not considering here for the reaction order, so that's the only difference. Okay, now for R minus 1, because we have K minus 1. So R minus 1 is equals to the K minus 1. So look at the arrow. Where is your arrow pointing backward? It's here. So with the arrow is pointing backward here, reversible chemical reaction, our reactant is already the ES. So K minus 1 times ES. Okay, times ES. Okay, now we go to segment 2 from here to here. So we have also our K2 here to produce this product, so K2. We don't have K2 minus 1 anymore because I said that is irrelevant and negligible because too few to consider the reaction or negligible enough not to be considered. So the velocity, the rate is 2 negligible. So there's no K2 K minus 2. Okay, unlike here, it's very stable, still having that K minus 1. So it's only 1 here. So rate 2, R2. So R2. So our R2 here is, look at the arrow in going there. So rate constant K2. So our reactant ES. See? So always take note, guys, that our rate law or rate of chemical reaction, which is the small letter R, okay, is equal to the rate constant times the reactant always. Reactant concentration, not the product. Okay, as you can see here. Okay. Now another equation here will be the total enzyme. So our total enzyme here will represent that as ET. This is ET, total enzyme, okay, is equals to, the total enzyme will exist as ES in the segment 1, okay, ES, okay, plus here E in segment 2. Actually, we don't need E plus P because P is another variable, is another product in which we don't identify yet. So it's only E, or meaning to say is negligible, the P, because total enzyme in segment 1, ET, is equals to ES plus E only, not E and P, because P is not related to the combination of an enzyme. It's another product that we don't know. So plus E, okay? This one. So this is a very important equation. This is a very important equation for our derivation of the Michaelis-Menten equation. Okay, guys. And then we have another equation to consider, like this. Okay, since we have this, okay, so this is from the product 1, here ES, product 1, ES, okay, and this E, somewhere along the way here in the segment 2, this is product 2, okay, like this. In terms of the enzyme, product 1 in terms of enzyme, and product 2 in terms of enzyme, that this is a free enzyme alone, solo flight. The P is not our interest here. It's not our interest, okay? Something like that. Now, this is our last and final reaction to be considered. The ET is equals to, okay, ES plus E. Now, we need also to establish equilibrium in here. Okay, this one. So this one, since this is the final chemical reaction involved for the total enzyme, okay, coming from here, so we have another equation from this, which is equal to E T is equals to E S plus 0. Why 0? This one. Because this E will become also negligible somewhere along the way. Okay? Look at the sequence. In the first chemical reaction, P will become the negligible or relevant part. That's why we don't have K2 minus 1. In here also, our E will become our negligible part. It will disappear somewhere along the way in the last final chemical reaction. So E as a solo enzyme will become 0 in the last chemical reaction. So what we have now in the last chemical reaction, E total is equals to ES alone. Okay, something like that. Now, we still designate K also in here, case. So we need to carry the K2 because this is happening more on the segment 2 here, segment 2, in which we have the E here and the ES. So ES and E belong to the segment 2 and the K2. So here our reversible chemical reactions also will be put in here. So this one is gonna be arrow going, this one, arrow going there. This is K2 because we are here in the K2 part. So K2, okay. And we have also the rate of backward reaction, which is supposedly K2 minus K minus 2. Now guys, this is K minus 2. Okay? K minus 2. Since this is an equilibrium stage, okay, and we have one reactant, which is ET, and one product, which is the combination of ES. So we can treat this as K2 is equals to K minus 2, or simply K2 is just equal to K2. So it is in the stage that we don't consider the negative, because there's no such negative sign for K in chemical reaction kinetics. It should always be the value of the number or numerical figure will be the negative, but not the unit of K, as you can observe. Going back to Eyring and Pagnoli equation, okay, and Arrhenius equation, if you can see that one, the K is not negative, okay, and the subscript is not negative also. So we will consider this as K2 is equals to K2 only. So in going here class, K, forward rate of chemical reaction, we have the initial velocity. Okay, and in going backward, we have also our V maximum, velocity maximum, meaning to say it is the highest velocity in which the chemical reaction will go to stop after achieving that V max. So after stopping the chemical reaction, our VO is equals to V max. So our initial velocity K going to K1, and our final velocity going to K minus 2, and then equilibrium with each other. So initial velocity is equals to V max, or R initial, which is the rate initial, O, is equals to R max also. Okay, like this. RO is equals to R max also. This one. RO is equals to R max also. Now, in here also, in this equation, guys, we need to see to compute for the R in this stage. So our R2, okay, our R2, okay, is equals in the forward. Our R2 in the forward is equal to K2, and our reactant is this, ET. So ET times K2 in going to the forward, so this one, K2, like this. This is our reaction. R2 is equals to K2 ET. Now this is also equal to initial velocity VO. So therefore, this is VO K2 AT. So our initial velocity is equals to K2 AT. Now we have also our, okay, R max here, R max. R maximum is equals to still K2 instead of K minus 2, because in equilibrium, so K2 is just equals to K2. Actually it's just the same, but by principle K2 and K2 forward and right is equal man siya, so there's no negative K minus 2. K2 is K2, so R max also is equals to RO. So our R max will be K2 again. So our R max here, rate maximum is K2 again, this one. But our reactant is another, because this is backward. So our reactant is ES. Okay? Okay. R maximum, okay, like this, is equals to K2 backward reaction. So our reactant is ES. Okay? Like this. So this is also equal our Vmax. Our Rmax is also equal our Vmax because this is the rate, or this is the Rmax rate, and this is also our velocity max. Okay, rate equals to the velocity initial. Velocity meaning speed over time. It's just the same as rate, but in terms of concentration is the rate. It's not in terms of velocity. But in here, we do not ask the same principle with the velocity. Okay, because it moves. The enzymes and substrates are moving somewhere in the chemical reaction. That's why it's still having the same principle, the velocity and the rate. But the point there is always time in the denominator. Okay, like that. So concentrations per time always. Okay, you get the point? So we have now, so Vmax is equals to K2ES. Okay, so this is also very useful. The Vmax, the VO, and this one also is very useful in derivation of Michaelis Menten equation. I explain this because we will be using this somewhere in our derivation, including these rates, Rs1, Rs2, R3, like that. Okay? That's gonna be the principle behind. Now, guys, I will teach you something somewhere along the way, another theory, but let's go now for the derivation. Now, in chemistry, chemistry lecture, especially if you're taking any science courses or college engineering courses, so we always remember the law of conservation of matter. Okay, what is that all about? Matter can neither be created nor can be destroyed by any ordinary chemical and physical means. Now, if we study thermodynamics and physical chemistry, that law in chemistry is still applicable, but it was converted to the law of conservation of energy. That states energy can neither be created nor can be destroyed, but it can only be transformed to various forms of energy. That is the second law of thermodynamics. The second law of thermodynamics is actually getting the principles of the law of conservation of matter in chemistry. Am I correct? Second law? Okay. I think it's not the second law, it's the first law of thermodynamics based on my stock knowledge. Because the second law of thermodynamics is focusing on the entropy part, that the entropy of the universe is always increasing, or the sum of the entropies of the system is always increasing, like that. So entropy of the universe is equal to entropy of the system plus entropy of the process, something like that, or the surrounding. It's gonna be like that, okay? But it is the first law of thermodynamics. Sorry for that. There's a lot of energies there, the heat energy, okay, the internal energy, and the enthalpy, something like that. First law of thermodynamics. The first law of thermodynamics is getting the principle from chemistry, the law of conservation of matter, and the law of conservation of mass. Now, it's also applicable here in chemical kinetics through that law of conservation of matter and conservation of energy, in which we will apply that in the equilibrium stage or steady state. Okay, we assume technically based on our concept for chemistry, steady state flow, chemical reaction equilibrium, that the rate of formation is equals to the rate of the products. Okay? Okay. The rate of formation actually is equals to the rate of deformation. Or dissociation. Do not be confused with the term. Be careful in chemistry. Okay. So this is our concept. This is our concept of steady state flow. Rate of formation. This is actually means the reactant concentrations, which we refer to enzymatic kinetics as our enzyme plus the substrate here. somewhere here. The rate of formation will be from here to produce here. Okay, so it will be equal to the rate of deformation over the rate of dissociation here. So after having the products here in this equation here, it will dissociate to E and P, something like that. The ES product coming from this reactants formation, okay, will dissociate into E and P in the last stage. It's equal to the rate of deformation. Now, your rate of formation is always the K1 here. Okay? Your rate of formation is involving the K1. So K1 involving in the first segment. Right? 1 from here to here. So we need to consider the R1. So rate, since rate of formation, that is R. Small letter R. So R1. Okay? Rate of formation R1 in the first segment. Okay? Now, it is equal to the rate of deformation. Our rate of deformation focuses in the two part, segment 2, including the initial part of ES. Okay, the initial part of ES that involves K minus 1. Okay, and this is the first step in producing or dissociating this to E and P. So it's gonna be rate minus 1. Okay, rate minus 1, it's in here, right? Rate minus 1, and then plus rate 2. This is our rate deformation, equal to R minus 1 plus rate 2, this one. Rate 1, this is for our first segment, okay, the first original reaction, equal to the R minus 1 is the rate of backward reaction in the first segment or our initial concentration, okay, and then plus R2, which is in our second segment too. Why we put R1 minus here or R minus 1? Because this is in the dissociating part, deformation part already. Okay, that's why we call it as a deformation or dissociation to convert that with EP here. Okay, in enzyme and products, it starts with ES, so that is backward K minus 1. So K1 is no longer that one, it's our formation, rate of formation. Okay, like that. So we use this individual R1 minus 1, R2 has its own corresponding equation that we already obtained here. Okay, the rates 1, rate minus 1, like that, and rate minus 2. We substitute that here in this R1 is equal to R. The value of R1 is here. Okay, is here. R1 is equal to K, concentration of E, concentration of S. Copy that. R1 is equal to K1 A S is this. Okay, is equals to R minus 1. R minus 1 here is this. Copy. R minus 1 is equals to K minus 1. Then E S plus R2. What is our R2 here? Our R2 here is this one. Copy that also here. Here. So we can complete the equation. Okay, R2 is equal to K2 ES. So this is the formal starting point of our derivation of the Michaelis-Menten equation that talks about the velocity of the enzyme and the substrate. This is our starting point of our derivation. Okay, this one. First step. Now let's do the derivation now. Okay, now since here, right, we have the E here. Okay, capital E as the enzyme. We use this equation also. ET is equals to ES plus E because there's an ET here. Solve for the value of E, capital E, because it's in here E. Right? E. So in here, in that equation, solve for the value of E, because we use this in the first step, starting point of our reaction. So it's gonna be, okay, ES plus E is equals to ET. So E is equals to ET, okay, minus ES. So we solve now for the value of E equal to this. Okay, substitute this E to here, E, and proceed the proper derivation. Okay, now K1, okay, K1 is equals to E, which is equal to ET minus ES, okay, like this, bracket, times S, like that, okay, then like this. So if we substitute that value, we can have now like this. Be careful with the putting of the bracket also, okay, because if you put wrong the bracket, then you will be wrong. So make it very, very smart to put the bracket and parenthesis very, very carefully, because it will meet the PEMDAS rule of algebra. PEMDAS rule of algebra, that you have to start with the parenthesis P or bracket, followed by multiplication, followed by division, and then fourth will be addition, and the last will be subtraction. PEMDAS rule in algebra will be applied here. Okay? So that be careful with the parenthesis incorporation or having the parenthesis, because somewhere along with your operation you will be wrong if your parenthesis will be not properly divided, whatever. You don't know how to segregate those variables like that, or coefficients like that. So be careful. So it's equal to, okay, K minus 1, okay, ES plus K2ES. Guys, take note, in here you have to do a lot of algebra here, but not a very difficult algebra, only distribution, multiplication. This one will be times here, and again times here, and this one also will be times here, and again times here, because this is common to both, because this is a parenthesis, overall parenthesis. So after you multiply this here, you still multiply this with here, S, because this is common to 2. And this one, you multiply this one also, and you multiply this K also because of the big parenthesis. So it will become now, okay, K1, distribution, multiplication in algebra, basic math. Okay, K1 is equals to AT S is equal also to K1 ES S. Okay, this one, if you distributed it properly, this will become like this. Be careful, huh? Is equal to this. In this side, we have the commonality of ES. Okay, ES commonality, factor that one, common is ES, and then you can say that one as ES times K minus 1 plus K2, like this. Okay, this is now our equation to be used. This is now our equation to be used in going to our Michaelis-Menten equation that deals with the velocity. Okay, it's gonna be like this. Okay, now solve for what is being required, and the common here is K1. Okay, K1. So this is gonna be divided by 1 over K1, the entire sides. So all sides, left and right, multiplied by 1 over K1. So that after multiplying 1 over K1, here will be simplified a little bit, removing the K1 part here. Okay, and here there's still K1, no problem, because there's only one K1 in the denominator. So it becomes like this. Okay, ATS, okay, like that, okay, and ES like that is equal to ES K minus 1 plus K2 over K1, this one. After multiplying both sides with 1 over K1, our result of our derivation is like this. Okay. Now, what you will notice this. Okay. In the left side, shall I say, left side, in here, in this side. In this side, so many K's involved. We have the K minus 1 plus K2 and over K1. So we leave this all K's, rate constants, commonality. So there is what we call one rate constant for this in physical chemistry. Okay, physical chemistry, because chemical reaction kinetics in here is under studying chemical reaction kinetics, which are all part of general chemistry lecture in your first year college. Because this was not taught in chemistry high school or in elementary level. This part is already taught in college, in first year college. Okay, now you remember in your general chemistry lecture, we have rate constant known as Km. What is this Km all about? Km. The Km class is talking more about on the enzymatic rate constant, the enzymes in our body. Okay? We have the catalysts inside our body, the same as the catalyst we have in the physical and chemical separation processes in various plants and industries or power plants, chemical industries, whatever. Because the purpose of catalyst is to speed up the rate of chemical reaction without being consumed and used up in the entire chemical process. Something like that. And then we have also an enzymes for human body. Our enzymes also are used to speed up the rate of biological substances chemical reaction in producing, for example, fats, nucleic acid, proteins, carbohydrates, steroids, acids, bases, okay, sugars, protein, okay, and a whole lot more. That's we call biological chemical substances or biochemical substances need enzymes equivalent to catalyst in the chemical plant processes to speed up the biological substances rate of reaction inside our body so that we will become strong, we will become healthy, we can survive in this world. Enzymes inside our physiological reaction of those biological substances and biochemical substances are very, very essential. Not only that, to produce hormones also for the communication for those various organs that they require this kind of hormone to be active like that. For example, in our brain, we need a caffeine stimulant to keep us energetic to think or to keep us awake like that. Very energetic caffeine like that. We have a lot. We have another is we have the adrenaline. Okay, something like that. That's our hormones, right? Dopamine, like that. What else? For sleeping hormone, we have also for the sleeping hormone, like that. Eating hormones, we need that also. Mood hormone, something like that. We need that also. Okay, so that is not our topic today. Hormone discussion. I already discussed that. There's a lot of hormones. I cannot explain to you one by one. Okay, but my point is, we really not need an enzyme to those hormones to actively participate in our physiological reactions in order for us to become healthy. The nutrients will be functioning effectively inside our body. Because without these enzymes, we will die. Because enzymes are really catalysts to have perfect biosynthesis inside our body in order our organs and cells inside our body will become healthy, like the liver, the brain, the heart, the kidney, the endocrine system, the heart, the cardiovascular system, the gut health system, or the digestive system. All of them needs enzymes. Okay? Without enzymes, it will not function properly. Then we will be affected. We will get sick. Okay? So this is also the same here. Okay? That's why we are studying this, because this is very important in biochemistry, enzymes. This is enzymatic chemical reactions. Okay? Like that. So going back. So we have now our equation like this. Now, so we are here, we're stopping here. K minus 1, K2, K1 is equal to the Km. The Km class is an enzyme's affinity to produce substrate. Like this. Okay? Enzyme affinity, meaning the attraction to the substrate. For example, in this equation, okay? The enzyme's affinity, meaning reaction, okay? The ability to combine, okay? The ability to attract, the ability to react with the substrate S. So we need that Km. That is the rate constant. We are referring to this. Okay? K minus 1 plus K2 over K1. This is very important. Without Km, then there will be no attraction between E and S. Okay? And then our organs inside our body will not function properly, because these are all about enzymatic kinetics inside our body. Okay? Because the other topics, Arrhenius, Michaelis, Menten equation, are process kinetics that involves catalysts, not applicable inside our body. But this topic, this Michaelis Menten equation, enzymes, same principle with catalyst, chemical reaction kinetics, but applicable inside our body. Okay? Different medium, human being, or the processes in the plant, factory, like that to produce chemical products. Okay, raw materials being added and mixed with each other to produce our products. We need catalysts there. That's another story, and this is also another story. We need catalysts inside our body, but the enzymes are the equivalent. So in order for us to understand well how fast and how slow the enzymes are reacting in the chemical reaction, we need to study this Michaelis-Menten equation. Okay? Specific for biochemistry. A combination of biology and chemistry. The study of the life plus the study of chemical changes inside our body. In the combination of those biological substances, macro biological substances, which are carbohydrates, sugars, nucleic acids, and proteins. Okay? And the rest will be, other various derivatives such as steroids, fats, oils, okay, acids, saturated acids, like that. We have the low density lipoprotein, high density lipoprotein, the cholesterol, okay? It will be produced also through enzymes reaction, okay? If our enzymes inside our body will be in total failure, then we will die. Okay? That's the purpose of Michaelis-Menten equation, that we have to analyze what's going on inside our body, right? So biochemistry is very interesting also. Okay? So for me, I like, because it's inside our body really, for our survival, rather than in the plant process, in the factory, okay? The factory will die, but me, I am alive because I'm studying inside my body, the biochemical reactions inside my body, which is the enzyme, not the catalyst in the process. Okay? For me lang ha, it is more important rather than that. Okay? Because I can have another job, not on the process, not on the plant. For example, I work in banking and tourism, like that. I don't need those catalysts, chemical catalysts. I don't need those processes there, physical, chemical separation processes. So I still have the money. But I have my body. I still have to know the chemical reaction kinetics inside my body so that I can survive. In this, there's a relation also how often we get sick, how often we get the diseases, because if we know the chemical reactions inside our body, okay, we can really think what's the best medicines for this, treatment, prevention, and we link that with the study of the epidemiology controls and prevention of diseases, because we know what are the chemical reactions inside our body. If we more of that, if we less of that, if we less reactions for that, we will produce this disease. If we more on that reaction, we will produce this disease. So it's related now to epidemiology, and that's why clinical chemistry will be arriving. Our health professionals will be arriving that. That's why pharmacy and doctors and medical technology have thorough and adequate knowledge of chemistry, clinical chemistry, medicinal chemistry, okay, like that. So they have to study chemistry also, combination of both, because all medicines are coming from the raw materials of different chemicals, plants, like this, and then they extracted the one to produce a medicine. Chemistry is there all the time in the analysis in the laboratory. Okay, so that's why chemical engineer, chemist, pharmacist, medical technologist, doctors, like that are very close with each other in terms of science, study of science, particularly chemistry. There, biochemistry. For us, biochemical engineering, because we are engineers. But the K term is bio plus chemical. Chemical is really have the chemical reactions there. Biochemistry in their part, biology and the chemistry. But we are more on the process, plus the application of the technology and mathematics. That's why engineering, and we have a design. But they don't have that, but they go for the detailed study of the theories and concepts of biology and chemistry, which is biochemistry, okay, inside our body. They treat, their client is always the human body. Their patients are the people, not the plant, not the factory, okay? But the chemical engineering is both, okay? The plant, the company, chemical and separation processes, plus the human body inside chemical reactions, because we need to study this also so that we can understand. That's why we have subject biochemical engineering. I think that is 2 semesters, no, 1 semester only. Biochemical engineering or biochemistry, we have that subject in BS Chemical Engineering. Okay? And also for the BS Chemistry. But our focus more on the design and application of technology and mathematics. Not so much on going detail to the theories, concepts. That's biochemistry now, that the BS Chemistry students are taking into consideration, okay, like that, and the BS Pharmacy, like that, or the doctors, whatever, they have chemistry, rigid chemistry, yes, but inside our body, okay? The health professionals are focusing on the chemistry inside the human body, okay, that's their limitation, but they cannot apply that in the plants, processes, company, factories, but chemical engineer are both, okay? You got the point? Both. We can deal also in the human body and then also deal also with the plant. Meaning to say some chemical engineers can work also in the hospitals because of chemistry thing. Okay? Because we can easily adapt and understand what's going on inside our body for the chemistry of oxygen, hydrogen, and a lot of chemicals inside our body. We are really familiar for that. Okay? That's why we can work both. Okay, they can also work also in the plant, but on the patients of the people when people got sick in the plants. We have also doctors and nurses there. Okay, but what I mean for the processes, okay, chemical reactions in both human body and in the plant cycle. Okay, like that. Oh, going back, we have now here. So we will put this as a km. What is again a km? A km is a rate constant. It's a measure of the enzyme's affinity, meaning a combination for its substrates. Because enzyme plus substrate always, and we need to determine the rate constant. Okay, this is km. So simplified already as km. It helps a lot to simplify our derivation. And now we can have this as total enzyme, okay, S minus ES times S, okay, is equal to ES, okay, times km na siya, class. Okay, km na siya, rate constant of enzyme's ability or affinity with a substrate. Okay. This one, a little bit simplified now. Now class, what do you notice here? This, okay, this total enzyme times the substrate. Guys, if you meet an open and close parenthesis, that is referring to a concentration. Okay, that it means like that in chemistry. Okay, if there is a close and open parenthesis, that means that is referring to a concentration. Okay, Like the expression of a concentration could either be molality, normality, or all types of solubility. Okay, the measure of the expression of the concentration. Okay, ganon. So like this. So this quantity minus this quantity. Guys, this ES and S, we don't need this in our entire chemical reaction, in enzymatic chemical reaction kinetics from here to here. We don't need this, guys. Okay, so what shall we do? If we don't need this, we need to eliminate this. What is the only way to eliminate this? If we add a quantity this in the whole equation, so that this will be eliminated. So this side will be added with this one, or this side will be added with this one, and this side also will be added with this one. Okay, like that. And this ET will not be added because it is the total already. Only this 8 ES and S will be added with the same quantity. Because this is already subtraction, it will be cancelled. Okay, and added also here. Something like that. Okay, so 80, so that we can cancel this second term, this. We don't need this in our enzymatic chemical reaction kinetics. In our chemical reaction, the purpose is to eliminate. That's why we need to add this quantity so that this will be eliminated. And if we add this also, we add also in the right side. It's the rule of algebra. If we add something to other side, add also something to other side. If we multiply something to other side, multiply also something to other side. If we multiply to the reciprocal of a quantity, okay, then multiply also with the reciprocal of the quantity. If you divide something on the other side, divide also with the other side. Both will be divided. That's the theory and basic concept of mathematics. Okay, because if you don't do that, it will not be balanced at all. Then you cannot meet the law of conservation of matter and the law of conservation of energy that has been discussed at the center of studying chemistry. Okay, that's the purpose behind why we keep on doing that. Okay, because if there's no purpose, then what's the use for this derivation at all? Okay, something like that. Okay, now we have this equation like this. Now, in my introductory part, I discussed a lot of principles and theories, right? So let's remember that one also. Where is that? Okay, it's here, right? Where is that? Here. This one. This is the time that we will use this quantities in this last derivation here. Because this is already a bit simplified. And then we have the values here in our introductory part I discussed first. That I told you we need to use this in our derivation. So we need to use that in here. Okay. Now we have ET, total enzyme. What is the total enzyme here in this reaction? This reaction involves ET, then algebra again. Solve the value of ET in this equation. Okay. ET, get that equation here. So, R, KT, KT2, ganon-ganon, chupa-chucho. AT is equals to R2 is equals to velocity O, or velocity initial. Okay, velocity initial R2 is equals to this equation, right? Like that. We are not concerned with the R here. We are dealing with V here in enzymatic kinetics. But in chemical reaction kinetics, we are dealing with R, not on the human body, on the processes. But in the human body, we deal with velocity V. Actually, it's just the same principle. We're just replacing with V. V initial is equal to our R, like that. Now, so we need to use this and solve for the value of K2 in terms of initial velocity VO. Now solve for AT. AT is equals to velocity O over K2. So this is our equation obtained. Okay. AT is equals to VO over K2 since we have ET here. Later we will substitute that here. Okay. Now, investigate and visually analyze what another. So we have also the ES. Okay, but before that we need to plus this with ES so that it will be cancelled as I promised. Charot. Okay? It's gonna be like this. Para di siya mulubog. Okay? Ganun talaga siya. In derivation, you have to add something to multiply something para di siya mulubog. So that it will never complicate and you can achieve a more simplified equation after all. So that's the main purpose. So it's very easy to understand. If we have a simplified formula and equation, that's our purpose, to eliminate those variables, right? Okay, so AT is times S, okay, and then S plus, as promised, S. Take note, guys. Okay, this one. ETS minus ESS, this is negative already here, right? Plus S, it will become 0 when you add that one. So 0 cancels out. Toing, 0. Ganon. Simplify na siya, kay 0 na siya. Is equal to ES times KM na. Okay, ES times KM. And now we have a very simplified equation out of those complicated equations. Then we have AT, okay, AT times S is equal to ES to KM. Now, so this is now our very simplified equation going to the Menten-Michaelis equation. This is not Menten-Michaelis equation, but this is now already simplified. And now, that is the time we will substitute this AT there, in here. Okay? Now, we still have ES here, as we can investigate visually. So, our value of ES here, still found in my introductory part of this vlogging. Okay? It's here also, ET, that involves AT, it's here. This involves ET and ES. This one, Vmax. Vmax is equals to K2 times ES, and solve for the value of ES, so that we can substitute also that here in the final equation that we derived. Okay, now, okay, so Vmax is gonna be like that. Vmax is equals to K2 ES. Solve for the value of ES, basic math. ES is equals to Vmax over K2. Okay, this is now also our second equation to be substituted here. Again, what is our AT? I already derived that. AT is AT is equals to like this, VO over K2. Okay, this one also substitute that here. Okay, see? The value of ET substitute in this equation, the value of ES substitute in this equation, so that we can achieve finally our Michaelis-Menten equation in enzymatic chemical reactions inside our body or inside the plants, animals, and living organisms. Not limited to human body, but all living organisms, plants, like that. Okay, plants and animals, biology. Plants, animals, we are also included in the animal because we are also the highest form of animal in our biology. Okay, phylum Mammalia is human being belong to that phylum. There are a lot of phylum. Phylum Vertebrata, o ganon. Phylum PC, phylum Amphibia, Reptalia, a lot of types of the kingdom of the biology. Okay, Reptalia, Amphibia, Feces, like this, Mammalia. Okay. So, we belong to kingdom or phylum Mammalia, the highest form of animal on earth. Okay? So, this is applicable, this equation, to all living organisms, including the plants. Okay? And the animals. Okay? So, it's very important also in the, fermentation industry and pharmaceutical industry. Okay? Pharmaceutical meaning producing different medicines like that, and also fermentation and producing beer, wine, whiskey, because it involves enzymatic chemical kinetics also. Okay, and our human body. Okay, like that. Like that. So we substitute na. Okay, so ET is equal to VOK2. Okay, times S is equals to ES, which is Vmax K2 times Km, like that. Okay, this one. Now simplified further, because this is having both parentheses with each other, then multiply this, VO times this, Vmax times this. Okay, we can now have the VOS, okay, K2, and then Vmax, K2, and Km. Like this. Guys, in mathematics, dot or period is the same as close and open parentheses, or small letter x. That is the operation of symbol of multiplication. The small x times the dot and the period, and the close and open parentheses or the bracket, the same thing, multiplication. That's why I put here the dot and the dot here. Okay, like that. Now, if you see like this, a fractional form in both sides that deals a lot of variable, then you have to do a crisscross multiplication rule in algebra again. We put x like that, and then there pointing there multiply, and there pointing there multiply. That's algebra. Okay, like this. I will put like this. Okay. Multiply this quantity to this quantity, multiply this quantity to this quantity, so that it will become simplified. That's the rule. Okay. Actually, I don't have to specify that one because it's only in our high school or elementary, but I have to specify in order we can understand very well. Okay, like this. So VO S K2 is equal to V maximum, okay, Km K2. Okay, like that. This is now our equation. Rearranging this equation, VO like this, blah blah blah, chuchu. Rearranging this and solve for the value of initial velocity. Okay, guys, in Michaelis Menten equation, we are computing for the initial velocity of the reactants, which are primarily the concentration of the substrate and the concentration of the enzyme. So we need to solve for VO, the initial velocity or the rate O. So VO is equals to, again, basic mathematics. So we need to multiply, divided by SK2. Okay? This one. We divided by SK2 so that it will become VO now. So cancel this one. Okay? And then this will become V maximum. Okay? Km K2 over SK2. Okay? Like that. Like that. So, okay. VO is K2 and then K2 V max Km. Okay, like that. So we now simplify this as cancel K2 like this. Okay. So VO like this. Like this. VO, V maximum. Okay. Times S over 1 plus Km. Like this. Okay. After getting that one, we have finally the equation like this after solving the VO. VO is equals to V maximum times S over 1 plus Km. Okay, like this. This is the final equation for VO. Okay, so that's the equation of Michaelis Menten equation. Okay, that's very clear, right? Okay, like that. So I need to make it clear because too much erasures in the last part. So I need to repeat. Anyway, we have the answer already because it's very, it's very dirty. I need to emphasize more clean. Okay, so I have to put this way. ETS. I know you understand already, right? I have to rewrite to make it very clean for you to see. Okay, it's equals to ES. Okay, like this. ES. Okay. Km plus 1. Okay. Like that. Okay. And then Et will be equal to VO over K2. And then ES will be, okay, ET, sorry, reverse, again error, again, too much dirty. I want to make it clean, okay? So ETS, sorry guys, clean, ES, like this, KM plus 1, okay, like this. Okay, like this. No need. You understand, right? Already, the more it will be lengthy if you will repeat it again. Okay? As long as we understand already. Okay, like this. You know, guys? Like, okay? That's very clear. Okay? So it's gonna be our calculation for this one, VO. Okay? Like that. Get the point or not? Okay. This one's very clear, huh? Okay. So this is our equation for Michaelis equation. VO is equals to V max times S over Km plus S. This one. Sorry, this one. VO is equals to V max times S over Km plus S. This is substrate concentration. Okay, velocity maximum, and this is our rate constant of the enzyme's affinity for its substrate, and initial velocity of the reactants, enzyme, and substrate. Okay, like this. Because I also forwarded to you, there's no S here. Okay, this is Km plus S, not Km plus 1. Okay, like that. Only writing problem, but the derivation is correct. Writing after you will error in putting the words like this, something. Thank you so much for watching this, guys. I hope you enjoy this derivation of the Michaelis Menten equation. Thank you so much. Bye bye. Good luck, everybody.